All right, hello everyone. Today we're going to talk about SVM, support vector machines, and this is a theory part. So for theory, we're going to do it in two sections. Part one, which is today, and then part two, we're going to go over the regression part on next class, class 15. So support vector machines. This is one of the most powerful machine learning models out there. Well, at least before the extensive use of neural networks in deep learning, SVM was the winner. Right? But more recently, when we're using deep learning applications, methods like neural networks, so they're kind of replaced by neural networks, but still they're super powerful, right? And so in general, when you have a relatively small size of sample, and then even if the question that you're dealing with is very, very high dimensional, SVM is super powerful. It's usually one of the winners among the machine learning models. But if your sample size is large, then SVM is going to be computationally heavy and expensive. So we would be better off doing maybe random forest. Okay, so let's talk about the big picture first. On the left, we have support vector machine as a classifier, and on the right, we have support vector machine as a regression. Or as a regressor. So as you can see, it can be used both for classification and regression. So this is one advantage of that, right? And but I want you to pay attention right away when you're focusing on the classification, unlike the logistic regression or KNN, where the output was probabilities. So in SVM, the outputs are 0, 1, or classes. So there's no probability. So we call it non-probabilistic model, right? So you might think that, okay, this is a disadvantage because SVM is going to treat 51% or 99% exactly the same. The answer is yes, right? So in SVM, there's no difference between 51% or 99% if the probability-wise you want to think about it. But on the other hand, when we talk about these hyperplanes, the further you're from the hyperplanes, the more confident that you are, this is a correct classification, right? So we can give it to SVM like that. Okay, maybe in that sense, we can say 51% is different than 99%. If it is further away from the hyperplane, there's higher probability that the class is, let's say in this example, it's blue versus green, right? So again, for today, we're going to focus on the SVM classification. Okay. So I want you to realize the distinction between classification versus regression, because when you look at these two graphs, you might think that, okay, these are exactly the same. We have a margin, then we have a hyperplane, we have margins in either cases, but be very careful, guys. Look at the dimensionality of the feature space. On the left that we're talking about the classification, your feature space is two-dimensional, x1 and x2. But what about on the right? What is the dimension of the feature space on the right for the regression? It's 1, right? Because this is your target variable, and this is your exponential variable. So do not confuse these things. These are completely different things, right? On the left, the classification, the goal is to find the hyperplane, and we're going to talk about the hyperplane geometry of SVM in general, but just as a big picture. The goal is to find the hyperplane that gives you the maximum distance between classes, right? And we have two classes, here, blue versus green. Give you the maximum gap, we call it maximum margin between classes, right? So this is the maximum margin between, let's say, green and blue. And the algorithm is going to find the W stars and B stars such that this distance, this perpendicular distance is going to be maximized, right? So this is the goal for classification. However, in regression, this is our regression, let's call it fit, right? So this is our regression, because it can be line or it can be nonlinear regression. This is your hyperplane. So at the end of the day, it will become our f hat of x that we're looking for. And in regression, the goal is to find this hyperplane such that the majority of the observations in the train set are within this margin, right? And this margin is defined by epsilon, right? So the epsilons are your tolerance level. So imagine if you want to, and you pass that tolerance level to the algorithm and says that, okay, this is my tolerance level is epsilon. Now ahead and find that hyperplane such that the majority of the observations are within the margin, right? So this is how the SVR or support vector regressors are going to find the hyperplane. So the question between classification and regression is the optimization is kind of different, and I want you to pay attention that do not confuse these margins and etc. with each other, because in one, both of them are 2D graphs. In one, this is x1 and x2. In the regression, it is x versus y, target variable. So do not confuse these things. All right. So that was the big picture. Now let's look at where we are in general when it comes to machine learning models. So we are still in the realm of supervised machine learning models. And now we are down to support vector machines, right? So for support vector machines, we can do both classification and regression. And here I use SVC, but which stands for support vector classifier, and SVR, which stands for support vector regression. But in practice, everyone calls it just simply SVM, right? These are the SVM, support vector machines. And we call them machines because depending on the kernel that you're using, each kernel will give you a separate machine. So that's why we call them support vector machines, right? Simply, if you change the kernel that you're working with, you're going to come up with a new model. So it's a combination of a bunch of models, right? And the goal is to find the best model that's give you the best performance. If it is classification, gives you the smallest error rate. If it is regression, gives you the smallest RMSE. Okay. All right, so what's the plan for today? We are going to start with the SVM geometry. So we will talk about what are hyperplanes, officially, and then we will talk about what is perpendicular distance, but because that's the key. When the model when the machine is doing the optimization, SVM optimization, the goal is to find the maximum distance between points, right? And we have to figure out how can we calculate the perpendicular distance between 2 points or between a point and a line and things like that. So we'll talk about perpendicular distance and hyperplane itself. Then we will talk about the motivation of SVM and why it is super powerful. And because we'll deal with these things that it can handle the nonlinearities, it can handle the outliers and things like that. Then in the next part 2, we will go over MMC, SVC, and SVM. So lots of terminology, I understand, but at the core of it, we are doing one thing. We're maximizing that gap between classes, right? And so MMC is maximum margin classifier. So the goal is to maximize that gap and basically maximize the distance between the margins. The difference between MMC, SVC, and SVM is how we define the margin. In MMC, maximum margin classifier, the margins are defined, we call them hard margin, right? We don't allow for any kind of misclassification. Then we see that, okay, if that's the case, sometimes the optimization that you're doing, there's no answer to that optimization. So we have to relax some assumptions. How do we relax the assumptions? By adding some slack variable to the model, okay? Again, we're going to talk about all this terminology down the road, but this is just a big picture. So instead of using hard margin, we're going to use soft margin. So if I go from hard margin to soft margin, we go from MMC to SVC, support vector classifier. And then we see that, so what's the difference between the two? Sometimes there is no answer. The data is non-separable. There is no answer if you want to use one maximum margin classifier. So we have to relax the assumptions. We use SVC. So in SVC it's linear. Your classifier is linear. Sometimes the data is non-linear, right? So how do you handle the non-linearity? We have to go beyond SVC. So we are going to use the kernel trick to figure out that when the data is non-linearly separable, how can we solve it with using the support vector machines or support vectors optimization in general. So as you can see, at the end of the day, there was a question, one of the students asked a question, which one should we use? Should I use MMC versus SVM? If SVM is always better, so why should ever use MMC? The answer is we always use SVM, support vector machine. And MMC and SVC are subset of the parameters for SVM. At the end of the day, we're going to look for different combination of parameters for SVM. And maybe out of that optimization, your best answer is going to be SVC, support vector classifier. Or maybe the best answer is going to be MMC, right? But we always, in Python or in application, we always use SVM, and we play around with the features of that function, right? For example, if I use a kernel function to be linear, it's not, we can call it SVC. These are just some terminology, right? If the sum of all the slack variables turn out to be 0, that's going to be maximum marginal classifier, MMC. But basically, the core of all of them is the same. Maximum, try to maximize the margin, the distance, the gap between the classification. So this is our plan for today. We're going to focus on classification. And the next class, we're going to focus on regression. And we talk about tuning hyperparameters. We will talk about tuning hyperparameters in classifications as well for today. But we're going to talk about the details in the next one. And finally, we will conclude this and this model by going over the pros and cons of SVM and then its applications in finance. Okay, so that's the plan. All right, so let's start with the geometry and motivation. So in geometry, let's see what is a hyperplane. A hyperplane is a subspace whose dimension is one less than of its ambient space. So what is ambient space? Ambient space is the space that each observation is surrounded by, right? So for example, if you're in 3-dimension, I don't know, if you put a dot, so I think we all are in our ambient space is 3-dimension, right? So X, Y, Z. And if you look at the line, the ambient space is 1-dimension. If you look at the line is 2-dimension. If you look at the dot, it's 1-dimension, right? So a hyperplane separates that space, the ambient space, into 2 subspaces. So this is very important, guys. So pay attention. By construction, support vector machine at the end of the day is able to classify your question into 2 classes. So by construction, it's a binary classification, right? So if you want to use SVM for multiple class classification, we have to do a tree, right? So we're going to talk about it next class, but I want you to be aware that like logistic regression that we said that it's designed for 2-class classification, support vector machine by definition is designed for 2-class classification, because this is how we define the hyperplane. Hyperplane is going to divide your space into 2 subspaces, two subspaces, right? So if the space is 3-dimension, the hyperplane is going to be in 2-dimension, which is a plane, right? So this is obvious, right? So for example, these are just some terminology. So in this 3-dimensional space, what is a hyperplane? This is going to be my hyperplane. The dimension is 1 less than the ambient space. So here is going to be 2 space. So it's going to be a plane. And as you can see, it's dividing the entire space into 2 subspaces. In this case, so let's say anything in the red area and anything in the green area, right? If the space is 2-dimension, then our hyperplane is going to be a line in 1-dimension. Again, it's going to divide the space into 2 subspaces. And if the space is 1-dimension, our hyperplane is going to be a single point. So this is not a line, this is a single point, okay? So our hyperplane is going to be a single point, which again is going to divide our space into 2 subclasses. All right. The next concept that we need to review is the SVM perpendicular distance, right? So this is how do we define the perpendicular distance between 2 points, or from distance between a point and a line, right? So the perpendicular distance between 2 objects in space is defined is a distance from one to the another, and that distance should be perpendicular. That line is good. Depending on what the dimension you're talking about. If it is, let's say 2-dimension, you can call it line. That distance should be that line should be perpendicular either to the line or to the observation. So here, if you're looking at it, if you're calculating the distance of a point, single point from the line, then we have to have this perpendicularity at this point, right? And let's say this is a formula or the functional form for this red line, ax plus by plus c. It can be anything, right? A, b, c are parameters, is equal to 0. And we want to calculate the distance of, let's say, x null and y null from that line, right? So from geometry, we know that there is a formula for it. So the proof of this is going to be a little long, but it's not that difficult, right? I can navigate you to it to some. I think I put it on the optional readings, the proof of perpendicular distance. So if you're curious how to derive this formula, just check it out. But what matters for us is that this is a formula for calculating the distance of this point x0 y0 from the line. And why does that matter? Because guys, remember, at the end of the day, support vector machines, we want to maximize the gap between 2 lines, right? Or between observations from a hyperplane. So we have to know what's the formula for that, right? So this is going to be our formula. So for example, let's say in our machine learning language, we can look at this line as our hyperplane. We can call it f hat of x. This is what we're looking for, right? At the end of the day, you want to quantify this f hat of x. And then these points or any points are on the classifications, right? So we're going to say that the distance of, let's say, point A from our f hat of x is going to be the measure of f hat of x Well, let's use capital X because it's maybe it's a vector, divided by the square root of the weights, right? Weight 1 plus weight 2, weight 3, and etc. We can show it like this: f hat of x divided by the measure of weight, right? So this is the measure of weight. Is that clear in terms of notation? Okay. So when I say the measure of weight, so what kind of distance are we using? You remember in terms of Euclidean, Manhattan? What kind of distance is it? Euclidean. This is Euclidean distance, right? Because we're looking at the square root of the W1 square plus W2 square. So this is Euclidean. It's just remember, SVM when you're calculating the distance between observations, we are using Euclidean distance. So right away, when I'm working on SVM problems, do I need to standardize the features or not? Scale the features or not? Do you remember I gave you the rule of thumb last class? Whenever you're calculating the distance between observations, so you have to do standardization or you use a scale version of the data. Does that make sense? Because let's say X, I don't know, the one is reported in $1 million and X2 is reported in percentage. It doesn't make sense to calculate the distance between these two observations like that. So you have to scale the data first and then do the SVM. So again, because you're using a Euclidean distance in SVM problems in general, you should, I can say you have to do the standardization. All right. So is it clear so far? You can, by taking the natural log, well, it depends. If your X variable can take negative numbers, you cannot do log, right? So I think it is safer to do standardization, take the average out divided by standard deviation, or you can do mean max scalar if you want to make sure that the variables are between 0 and 1. We're going to talk about it maybe at the end of this class. We will talk about different normalization and standardization and which one works best. In practice, usually standardization works best because mean max scalar is very sensitive to outliers. So depending on what kind of data set you're dealing with. But it is safe to say that standardization is going to be the best performance among all of the scalings. Okay. All right. Now, so before going to the definitions of the optimization problem or classification in general, let's see again one more time. What's the idea of support vector machine as a regressor and a classifier? So as I said earlier, SVMs are very powerful and one of the most popular algorithm in machine learning. And it is a powerful supervised algorithm using classification and regression. So. And again, the neural networks have replaced SVM in many applications, especially when it comes to image recognition. So SVM used to be applied to image recognition or text mining and questions like that. But after neural networks were computationally feasible, nowadays we just do neural networks or convolutional neural networks when it comes to image processing, right? But still SVM is very powerful in any other kind of applications. All right, so this is starting with the classifier, just the big picture idea. The idea is that to come up with the margin that separate these two classes by finding the hyperplane, right? So I can say, so for example, I can say, okay, this is, let me actually see if I have, yeah. So for example, we can say this line can be the hyperplane, right? So if I pick that hyperplane, the margin between green and red is only this number. So this is going to be the margin. Maybe this is not the maximum margin between classes that I can imagine, right? So this is one example. Another one is, what if we take this one as a hyperplane and the margin? So it's trying to maximize the margin, but as you can see, the margin here as well, it's not maximized, right? So maybe the third one, we can say that, okay, let's talk about this one. Let's say that this is the best hyperplane out there, which is going to give the best classifier because the distance between the classes are maximized, right? Because the margin is maximized. So I want you to pay attention. Why do we care among these three, right? Among these three, why do we care that we should come up with the hyperplane that maximize that margin? So why do we care about that word maximum? Yep.
Does that allow you to get like the best model, like predictive model, to be able to classify your test data?
Yeah, exactly. So the key term is that this is training data, guys. Remember, we hope that by finding the maximum margin between observations in the training data, there's a higher chance that if I throw test data at this, still it's going to work. So we say that we want to find the maximum margin because it's more robust, right? If you go from training data to test data, there's a still chance that that classification is going to work, right? So that's why we look at the maximum. Because if you look at the train set, if you're only interested in the train set, frankly speaking, any of these three is going to do the job, right? But we want to go beyond train set because we don't care about the train set. We want to see how the model is going to perform on something that it hasn't seen before. So the answer is going to be this hyperplane. So that's where the word maximum is coming from. I just wanted to pay attention, where is this maximum? Why do we care about that maximum margin classifier? All right, and for regression, the same story. So we went over the intuition of the regression, but just one more time. The goal is to find a hyperplane such that the more observations are within the margin. And for that margin, we have to specify the errors. This is our tolerance level, right? So you specify your tolerance level. And because, for example, you can relax these epsilons to be very large, and then probably most observations are going to be within that margin. But we know that if that's the case, the model is super biased, right? The bias is high, the variance is small, and maybe that's not something that we're going to that is going to give us the smallest RMSE. There's always this trade-off between bias and variance. And I think by now you're completely familiar with that concept.
Is that for linear regression only or for non-linear?
Oh, very good. So for example, we're going to talk about it next class, but in short, yes, SVM, when we are adding the kernel functions, it goes beyond linear to nonlinear. So for example, if this is a regression, if this is your data, right? Something like that. That's a very good point, Abraham. If the epsilons are very high, so I can say maybe this is one regression, right? If I reduce the epsilons, right, then the model has to capture something like this in order to make sure that the crosses or observations are all within that margin. Then I reduce the epsilon, right? But very good point. SVM is very powerful because it can give you the nonlinear regression lines as well. All right. So let's start with the classification. And we're going to focus on the optimization problem for classification because it's easier to see. And then the next class, we'll see that the optimization between support vector regression and classifications are very, very similar to each other. So we will focus on the classification part today. Okay. So we're going to start with MMC because that's the most basic one. So we will see the idea of the hard margin and how we can because visually it's easy, right? When you look at the support vector machines, visually it's very easy. But how can I make it to an optimization problem? So how can I write these things mathematically? Yes, Ryan.
Sorry, can we go back to that last slide, the motivation, SVM motivation? Yeah, that one. So when you're doing this, the threshold is that the thick line, you're just trying to maximize the margins to get the best fit line. Is that what you're doing?
For the classification, yeah.
For the classification. And then when you are going through the test data, it's all about that thick line. It's not necessarily about the margins, right?
Yeah, well, in the test data, when you're done by finding the hyperplane, you're done, right? You don't care about these margins anymore.
Okay, yeah, that's what
right. So in the test data, if it is here, it's classified as green. If it is here, classified as red. Here, classified as green.
Gotcha. Okay. Yeah.
But again, we're going to talk about what do we call these points. We call them support vectors and why and how the optimization is done. But this is all in train set. When we're done with training the model, very good point. When I'm done with finding the W stars and B stars, that's it. I can find the formula for this function, for this classifier, and now I can just throw data at it.
And you don't need the margins anymore.
Oh, there's no margin anymore.
Yeah. Okay. Gotcha.
Yeah. All right. So we're going to start with MMC because, as I said, it's most intuitive, and then we'll see that what are the caveats of MMC. We have to go beyond that. And then SVC, we're satisfied with it, but still we see that, okay, there are some questions that SVC cannot handle. So how can I improve that? So I just want you to think of it that SVC is an improvement to MMC and SVM is an improvement to SVC. And in application, again, they're going to use SVM all the time. Okay, starting with MMC, maximum margin classifier, or we call it hard margin. So this MMC is a hyperplane that among all the separating hyperplane out there, in the example of classification, we saw 3 of them, right? So among all of them, it will find the one that makes the biggest gap, biggest margin between 2 classes, right? So if you want to just make sure that we understand the terminology, so this line is going to be our MMC, maximum margin classifier. Then we have observations. Let's say class 1, class red, we have to the left of the hyperplane, class green is to the right of the hyperplane. And guys, I'm not going to call this one line. I want you to get used to call it hyperplane, because in real world, we're working with higher dimension than 2 or 3, right? So a hyperplane can be a single point, it can be a line, it can be a plane, and it can be something beyond imagination of human brain, right? So just get used to calling it hyperplane. So this is our maximum margin hyperplane because it's separating green and reds here. And the points that are right on the right on the margin, these are the margins, right? So this is margin, this is margin. The points right on the margin, we call them support vectors, right? And the reason that we call them support vectors is that because the entire optimization, the entire, in this case, the slope of classifier, or if you want to call it slope, depends on these support vectors, right? So MMC is super sensitive to the place of these support vectors. So for example, if I have a green here, then this is going to be completely something like this. Does that make sense? So it's very sensitive to the support vectors, right? So I want you to realize that MMC in general is not sensitive to observations here, far from the hyperplane, or here, but it's super sensitive to the place of the observations on the support vector, right? So if I don't know, if I have just only another red circle, red observation here, then my entire, maybe this is not max anymore. If I have something here, this is going to be max anymore. This is going to be the new max margin, right? So you see how sensitive the hyperplane is to the observations on the support vector. Okay. All right, are we good in terms of terminology? All right, now let's talk about the core, the engine, what's inside the optimization problem for MMC. This is very, very important. I want to slow down a little bit and make sure that everyone understands, everyone is on board. Because if you understand this one, then you'll see how we can extend it to SVC and then how we can extend it to SVM. Okay. All right, so the core idea of hard margin is to maximize the margin. So we're talking about the hard margin, under the constraint that the classifier does not allow or make any does not allow for any kind of misclassification, or does not make any mistakes. So what does that mean? No, we are super restrict. We say that the classifier that you come up with, there should be no tolerance, right? So both classes here in blue and green should be completely separate from each other. You do not allow for any kind of misclassification within the margin, right? So that's why we call it hard margin. So if that's the case, let's see how can we, again, visually it's easy, so we can come up with this line, but let's see mathematically, how can we come up with these constraints, right? So let's put some mathematics into it. So SVM tries to pick the most robust model. And when I say most robust model, the one that is going to maximize the margins. By finding the W stars and B star. At the end of the day, the solution to this optimization is a bunch of W stars and B star, so you can find the shape of your classifier. And if numerically, so let's play around with these things. And these are all, again, guys, we do, for example, we call the blue class here -1, and we call the green class +1, just for simplicity, right? In order to make sure that we can translate all these features to mathematics. You can call it 0, 1, but if you do 0, 1, you have 2 constraints in your optimization. But if you do it -1, +1, we can merge it to one constraint, right? And the less constraint you have in the convex optimization, the better. This is just for convenience. We call them -1 plus 1. You can call them, I don't know, 1 plus 1, 10, whatever numerically you can call them. You can give them whatever value you want. But mathematically, it's going to be simpler, and you're going to see in a minute why, that if we call class blue -1 and class green +1. The reason that I'm emphasizing is that because you're kind of used to see default 1, non-default 0, something like that. In SVM, we call it 1 minus 1. It really doesn't change anything, right? But mathematically, it helps us to come up with fewer constraints when it comes to optimization. So the blue ones are, we can think of them as +1. Again, if you're defining the constraint like this, and the green ones are -1. Imagine, let's say this number. There's x1 and there's a x2, right? If I plug these numbers into this equation, I'll get some number greater than 1. Maybe it's 3. Yeah. Maybe it's 2, maybe. The further you are, the larger that number, okay? Okay, let me erase all this extra stuff. Okay, the eraser doesn't work, anyway. Yeah, now it works. Okay, so let's keep the one that we definitely need. So again, to just make sure that we're doing it correct, here's -1, here's +1. All right, now I can combine these two constraints in one. So let's see how we can do that. If I multiply both of these equations by y, then I can summarize it to one equation, right? So this is the optimization problem that we have at the end of the day. So just pay attention. If this yi is equal to 1, we know that this is the constraint. So basically, yi multiply this constraint is going to be greater than 1, right? And if yi is equal to -1, then when I multiply to this, if I want to multiply the right-hand side by -1, it's going to change the inequality to greater than or equal to 1. Does everyone see that? So basically, this is just for simplicity. We're going to say, let's multiply yi to these constraints, and at the end of the day, you're going to deal with only one constraint instead of two. This is how we define that, right? So this is going to become our constraint. So the whole reason that we did y is equal to 1 versus -1 was at the end of the day, we come up with one constraint in our optimization problem. So this is the constraint, okay? And now instead of maximizing the margin, you're minimizing the 1/2 of w squared of the measure of w to the power of 2. So why that's the case? I want you to realize what's the relationship between maximizing the margin and minimizing the weights. The measure of the weights, right? So for this one, we need to go back to the definition of hyperplane, right? So if I want to calculate the distance, perpendicular distance of, let's say, this blue circle from the line, what was the formula for that? We said, okay, it's equal to the measure of f hat of x divided by square root of w1 plus w2 to the power of 2, right? So I can write it like this. The measure of w. Is that clear to everyone? Okay. So the perpendicular distance for this blue circle from the line is this equation. And what is the perpendicular distance of the margin? So I can simply multiply it by 2, right? So here is perpendicular. If I multiply it by 2, I get the distance between the two, right? Okay. So the goal is to maximize this distance. So this is our margin, right? So do you see that maximizing the margin is equivalent to minimizing the w, the measure of w? Because w is in the denominator. If I minimize this w, I can maximize the margin. Does that make sense? Okay. So instead of writing, we can write a maximization version of it. You know, actually, if you read the ISLR textbook, Tipshirani, Hasey, they propose this, exactly the same problem, but instead of minimization, they do maximization, maximizing the margin. But I prefer to work with minimization because in Python, what you're going to see is minimization problem. Okay. So and they're exactly the same. If I minimize the measure of weights, it's exactly the same as maximizing this, the margins, right? So again, instead of minimizing this one, the measure of W, I'm going to minimize 1/2 of W to the power of 2. Because guys, remember, if you minimize a linear function, it's the same as if you minimize the quadratic version of that linear function. It's monotone transformation, right? If you look at the derivative, it's strictly increasing, so it really doesn't matter if you minimize W or W squared, right? And then this 1/2 is not going to play any role when it comes to minimization. But why do we put it there? Because if you take derivatives, it's going to make your life a little easier when you want to come up with a closed form solution for this optimization problem. Okay. Okay, so at the end of the day, what you need to take away from MMC optimization is that we are minimizing the weights, the measure of weights, and at the same time such that we satisfy this constraint. What does this constraint mean? Is that all the observations outside of the margin should be classified correctly, right? You're not allowing for any kind of misclassification within the margin. So this is called hard margin. So is this optimization problem clear? We're not going to talk about how we can, well, there's an appendix that I put, that I added to the slides, but, and we can slightly go over it, but it's beyond the scope of the class. So this is a convex optimization problem. It's well defined, and we can take derivatives, write the Lagrangian version, and we can calculate with a closed form solution for W star and V star. So here's a question for you. If there is a closed form solution for W star and V star, so what does that mean? Do I need to use gradient descent to find the W star, V star? From our previous classes? No, right? So the beauty of SVM is that it's guaranteed that, again, depending on the linear separable, if the data is separable or not separable. But if there is a solution for that, we can come up with a closed form solution. You don't need to use gradient descent to find the W. It's unlike the logistic regression. Do you remember in logistic regression, we have to use gradient descent because MLE, when we want to calculate the maximum likelihood estimator, we had to, there was no closed form solution. So the beauty of SVM is that there is a closed form solution. So in that respect, it's going to be faster. So this is a positive side, but the negative side is that sometimes this constraint cannot be satisfied. So that's why we have to go beyond MMC. We have to do, for example, SVC. Okay, so this is really important, and I want to make sure that everybody understood it. So is the optimization problem clear? What we're doing, we're minimizing the weights by satisfying two constraints. We can just squeeze it to one constraint. And what does this constraint mean? It means that all the classes, blue versus green here, should be classified correctly. It means that there should be outside of the margin. There is this model, this MMC does not allow for any kind of misclassification or violation within the margin. Okay, so this is the MMC. Now let's see why MMC does not work sometimes, right? So the MMC optimization, let's see. Okay, so the MMC optimization problem becomes infeasible whenever the conditions cannot be satisfied. And the condition, or we're talking about this one. Sometimes this cannot be satisfied. Let's see what are the cases that this condition cannot be satisfied, right? And this means that there's no simple line that can perfectly separate the labels. And MMC, just remember, guys, this is linear, and you want to make sure that there is one line there that can separate the entire classes to two parts, right? So we say that this cannot happen in a couple of cases. First, when the data is noisy, and when the data is noisy, we can still use MMC and find a hyperplane, right? But that hyperplane is not going to be robust. It's going to be very sensitive to outlier. So look at that. If this is the data, and I'm going to say this line is my hyperplane, I call it MMC, maximum marginal classifier. And what are the support vectors? So the support vectors are these ones, the vectors that are right on the margin, right? Okay, so we can use that optimization problem, give me back W star, B star. At the end of the day, I have a perfect classifier. It seems that it is perfect. But what if there is an outlier in this data set? What if I add this blue dot here? If I add this blue dot here, the entire MMC is going to be rotated very sharply. Does everyone see that? Because again, if you pass this new information to the data, the optimization is going to find a classifier that there is no misclassification within the margin. So for that reason, it's going to change the slope, in this case, W1, W2, very drastically. And so that's why we say that, okay, MMC is not robust. Does everyone see that the MMC is not robust? It's going to be very, very sensitive to outliers. So this is not good, right? So if I could somehow tell the optimization problem, tell the algorithm, ignore this one. If I could somehow tell the computer that they ignore this line, then it will give me the same MMC. And I know that the initial MMC is going to be more robust compared to the other one. Does that make sense? So that's one case that we want to go beyond MMC. We want to relax that hard margin assumption. We don't want to make it soft. Okay. We want to allow for some misclassification. So this is one case. Another one is that you cannot use MMC, right? Guys, remember, on the left, you can still use MMC, but it's not robust. On the right, you cannot use MMC. I want you to pay attention to these, let's say, blue and reddish circles. And can you come up with the hyperplane? Can you come up with an MMC classifier, maximum margin classifier? Look at that. Give it a try. I don't know. So for example, there's literally no way that I can come up with a hard margin, right? Does everyone see that? So whatever I do, there's going to be a bunch of misclassification at either. So as you can see, there's no answer to this optimization. Oh, let me go back. To this optimization, if the data is something like this. We call it non-separable data, overlapping data, right? So if that's the case, what should we do? In MMC, there's no answer. So you have to go beyond that hard margin. You have to relax that hard margin, right? So let's see mathematically, how can we relax that margin? Again, visually it's easy. I say, okay, allow for some misclassification, and then maybe this is your, at the end of the day, maybe this is your margin. I'm allowing for some misclassification. At the end of the day, maybe this is going to work, but let's see mathematically how it's going to work. Okay. So the solution to that problem is we can extend the concept of separating hyperplane in order to develop a hyperplane that almost classify the classes, right? Not, and by almost we mean that it allows for some misclassification, right? So, and we call this generalization SVC, right? So the previous one was MMC. If I generalize it by going from hard margin to soft margin, we just give it another name. We call it SVC. Okay. And the idea is that it can be worthwhile to misclassify few observations in order to do a better job in classifying the remaining observations, right? So this is the whole logic of going from hard margin to soft margin. Okay, look at a couple of examples. Imagine this is the data. I have 10 simple observations here, right? 1, 2, 3, 4, 5, 6 are red, and 7, 8, 9, 10 are blue. These are some observations in X1 and X2. And guys, pay attention. Look at X1 and X2. It's scaled, right? Here between -1 and 4. Next one between -0.5 and 2.5. So it is a scale, and it is important to scale the features because of we are using Euclidean distance. Okay. So in this case, I want you to pay attention. Imagine we don't know the answer. Imagine this is not the hyperplane. If I want to use hard margin, what is the answer? So what are going to be the support vector? Can you look at this data, this 10 observation, and tell me that if I want to use hard margin, what are going to be the support vectors? Give me numbers. 1 and 8. Does everyone see that? Okay. So if I solve this problem using MMC, maybe the answer is this. Something like this. That gives me the maximum margin, right? But here we are going to say that let's allow for some misclassification. And by misclassification, we mean that either on the wrong side of the margin or on the wrong side of the hyperplane. So here, we're going to talk about, in this example, you will see that some observations are on the wrong side of the margin. So this is the margin. This is the margin. And this is your hyperplane, right? So can you tell me that which observations are on the wrong side of the margin? 1 and 8, right? Is there any observation on the wrong side of the hyperplane? No, right? Okay, so why did I go from this one to the new one? So in other terms, why did I go from MMC to SVC? This is the SVC. Why do you think we did that? No. Well, the margin is going to, in both cases, the margin is going to be maximized depending on how you define the support vectors, right? So if I use MMC, the distance between 1 and 8, if I maximize it, this is going to be my MMC, let's say. If I use SVC, because the support vectors are different now, still the margin is maximized. So the answer is not we want to maximize the margin. The answer is something else.
Is MMC sensitive to all wires?
Yes, that's a good one, because MMC is not robust, right? It is super sensitive to the position of 1 and 8 now. If I simply, look at that. If I simply change this, imagine the observation. So the support vectors in MMC are 1 and 8, right? If 8 was here, then it's going to drastically maybe change this one. Or if 8, or yeah, maybe it's something like that. If 8 was here, or if 8 was here, you'll see this, the maximum margin is going to be something like this, which is completely different, right? So you see, because if I use the 1 and 8, if I use MMC, the support vectors are going to be 1 and 8, but it is at the end of the day, it's going to be super sensitive to the position of the support vectors. So because you have only 2 support vectors in that optimization problem, it's going to be super sensitive to the position of that, right? In other terms, we're going to say that MMC is going to overfit the model. It's very sensitive. The bias is going to be small, but the variance is going to be large. And you see why the variance is large, right? So for that reason, on this graph, we want to go from MMC to SVC, right? And as you said, there are 2 misclassification. And by misclassification, I mean they're on the wrong side of the margin, right? Now, let's look at another example. OK, so for this one, I can literally not use MMC. Does everyone see that? So I added 2 new observations. I added 11 and 12. So 11 is here, 12 is here. So if you add 11, which is red, and 12, which is blue, you can literally not use the MMC. So in this setup, you have to use SVC. So you have to use the soft margin. OK? And guys, here, still, you're using soft margin because you're allowing for 2 kind of misclassification on the wrong side of the margin. Okay, on the right-hand side, so here's a question for you. What observations are on the wrong side of the margin?
1 and 8 and 11.
So wrong side of the margin, so here, this is the margin for red. This is the margin for blue, right? So wrong side of the margin for red is 1, and then we have 11. For blue, there's 8 and 12, right? So these are on the wrong side of the margin. Which observations are on the wrong side of the hyperplane? 11 and 12, right? So 11 and 12 are on the wrong side of the hyperplane as well. Okay. So we allow for this misclassification. So this is completely misclassified, right? So 11 and 12 are completely misclassified because they're on the wrong side of the hyperplane. 8 and 1 are not misclassified, but they're on the wrong side of the margin. Are we good? In either case, we're allowing for some kind of, we're allowing the model to make some mistakes on purpose. Yep.
So 11 and 12 are misclassified.
Yes.
1 and what do you call 1 and 8 again? Sorry.
They're not misclassified. They're on the wrong side of the wrong side of the margin.
Okay.
So earlier I said misclassification in the sense that they're on the wrong side of, but misclassification terminology, they're not misclassified because look at that. At the end of the day, this is your hyperplane. This is red. This is red. And this is blue. So they're not misclassified, but they're on the wrong side of the margin.
So there's not a special terminology?
Not that I know of. You're just on the wrong side of the margin. Yeah.
If we assume, so Rodney, I was just going to ask, you may have mentioned this already, but do we manually set the size of the margin that we're looking at, or is that right? So like the distance from the hyperplane to each.
The margin is, well, we don't manually, if you look at the optimization problem, it's a good question. So we want to maximize this margin, right? So that margin is going to be solved. That number is going to be solved at the end of the day, right? We know that among all those hyperplanes that we can think of, there is one that's going to maximize the margin. Right? But here we are adding the idea of soft margin. So, and mathematically we have to do something about it, right? Because we are not there yet. Optimization is going to be slightly different. Okay. And Abraham, question?
Yeah, the question was, so if 11 and 12 were actually correctly classified, and you said 1 and 8 are not misclassified, they're just out of the
On the wrong side of the margin, yeah.
Does that in any way affect the predictability of?
No, actually, that affects your optimization problem. We're going to look at that. So there's something we call the slack variable. We're adding those slack variables, right? So, but let's look at an example and hope it makes more sense. So visually, we know what to do. We basically need to go from hard margin to soft margin, somehow widen that margin. But mathematically, let's see how it's done. So soft margin classification adds a penalty term. We call it C. Think of it as a cost function to the objective function for observations in training set that are misclassified, right? In essence, the SVM algorithm will choose a decision boundary that optimizes the trade-off between wider margin and lower total error, right? And basically, the idea is that, let's see, there's something, we call it xi, or I don't know, people call it xi, it's a Greek letter, and even some people call it kesi, but I think xi is more commonly used. So this variable is, let's call it xi, and this is a slack variable. The slack variables allow observations to be on the wrong side of the margin, right? And we're going to penalize them. So it's okay, on purpose we allow for some of these misclassification, but it has a cost, so let's penalize them. So this is the whole idea, right? And if, for example, look at these. Look at this observation. So here, the red one, let's call it psi I, and here the green one, these are misclassified, right? It is okay to have misclassification, but you know that it comes with a cost. So let's add that cost to the optimization problem as well. Because we're using a minimization function, so we can add a plus version of this cost function to the term, right? So what are we doing? It says that, okay, do the same minimization problem, minimize the weights, but add a cost term to the sum of these slack variables, right? So what is the sum of these slack variables? Basically, the sum of slack variables is the total distance of points on the wrong side of the margin. You're adding all of them together and you're penalizing them. Does it make sense? So this is the objective function. So in terms of objective function, the same minimization problem, but because you're adding some slacks, that slacks comes at a cost. So let's add that cost to the model as well, right? What happens to the constraints? Exactly the same constraint, but look at that. You're subtracting these slack variables from the right-hand side. So what does it do? So it says that, so for example, look at this observation. Look at the first one. Here, we are going to call them +1, -1. And then it says that all observations on the right-hand side should be greater than 1, but not necessarily greater than 1. I'm allowing for some slack. Give me some slack. Does that make sense? So it's 1 minus that slack term, right? The same story for the observations on for the green one. So all observations should be the less than -1, but not necessarily completely less than or -1. Give me some slack. So except this one as well. Does that make sense? So this is how we define the soft margin. So it's not hard margin anymore. We are allowing for some misclassification by using soft margin, but we are penalizing that by adding the cost term to the model. So before going to the next slide, I want you to conceptually think about it. If I increase this cost, what will happen? The margin is going to widen or going to narrow or wider? If I increase the cost, it's going to get narrowed, right? Because you're telling the model do not allow for any kind of misclassification, so the margin is going to get narrower and narrower. Yep.
Just to clarify some terminology, so going back to the previous slide, numbers 1 and 8 and 11 and 12 would be slack variables.
Here, the one that are misclassified only, right?
Oh, okay, so just 11 and
Yeah,
12.
yeah. This is your Kessie I, Kessie, let's say J, whatever.
Okay, so the cost and the penalty is only to, it's not to the margin, it's to the actual.
Yeah, because think of it this way. At the end of the day, we know that these are going to be within the margin, let's say here 1 and 8, but it's not misclassified. So let's not penalize the model for that.
Okay.
But it's within the margin. But
Yeah.
there's no need to penalize them.
Gotcha.
But these guys are completely misclassified, so let's penalize them.
Gotcha.
So when you're penalizing, what are you doing? What is the model doing? Is it just taking out the weights of those observations, or?
It's doing something like that. Well, at the end of the day, if you're adding this cost to the model, the W's are going to be different, right? Because look at this one. Let's talk about this cost of misclassification. I tried to answer your question here. So let's talk about the regularization parameter. So this C, cost function, cost of misclassification, we also call it regularization parameter. So which one do you think has the smallest C? Which one has this largest C? Can you look at, so for example, here, this is the margin, very, very wide. Here, this is the margin, very narrow. So give me C. C is large or small here, in the first one. C is small. The cost of, so look at that. Give me a lot of slack, right? You say that it really doesn't, as long as the cost of slack is small, you're going to make that margin wider and wider, right? So here, C is going to be small. Compared to here, which C is large. So if C is, so Abraham, back to your question, how does this C is changing the output? It's basically changing the W1, W2, right? Because if your margin is wide, so this is your hyperplane. If your margin is narrow, this is your hyperplane. So the algorithm, when it's solving these things, is going to go over different combination of W1, W2, and B in order to satisfy all the conditions here. Okay. So when C is small, we have a wide margin like this. If you have a wide margin, what is high? What is bias? Bias is going to be high, right? Because on average, we're not hitting at the target. And what about the variance? The variance is going to be small. Because look at that. If the margin is super wide, the variance is almost zero, right? And on the other hand, when C is large, we have a narrow margin. And it means that the bias is low and the variance is high, right? But if you make this C very large, are you overfitting or underfitting? I'll get to your question. If C is super large, you're overfitting, right? So this is overfitting the model. David.
Just a couple clarifications. For C, essentially we can think about it as the cost of 1 point being misclassified, and then we total that all up.
The aggregation of all the misclassifications, right? Yeah.
And then we set that value of the individual
Yes,
cost.
yes,
Okay.
yes. We said that manually. Okay. So it can be 1, 0.1, 10. You use a grid search in Python and figure out what's the best one. Again, at the end of the day, it's a combination of, it's a trade-off between bias variance, right? So so for example, I know for a fact that this is going to be overfit, this is underfit. So maybe this one and this one, which is the better one? The one which gives me the smaller error rate or higher accuracy in the cross-validation version type. Okay. Okay, yeah, sure. So this is, now, so we covered the MMC, we covered the SVC. Now let's see, what if the data is like this? The data is non-linearly separable. Can you think of any kind of classifier? So if I do something like this, huge amount of misclassification on either side. Do you see that? So I cannot come up with any kind of classifier, either well, hard margin, not at all, even soft margin. If I increase that C, so regardless of the value of C, I cannot come up with a linear classifier. Does everyone see that here? So what is the answer? The answer is if you can somehow come up with a nonlinear classifier. This is the answer, right? So let's see how we can get that, right? So mathematically, we can solve this problem by going to higher dimension. So right now we are in 2 dimension, right? So we have the blue and red. We are in 2 dimension. So how can I mathematically solve this? If I go to higher dimension and then find the hyperplane in the higher dimension and then project it back to lower dimension, then I can find my classifier. Does that make sense? So let's look at it visually. So if I go to higher dimension, so from 2 dimension, we go to 3 dimension by just using a mapping function. That mapping function, so in this case, it seems to me that maybe it's a quadratic one, right? So we're seeing something like this. So maybe z squared is equal to x squared plus x1 squared plus x2 squared. So we'll give you something like this. Does everyone see that? Okay. And then now in 3 dimension, I can easily come up with my hyperplane. Does everyone see the green is a perfect hyperplane? It's able to classify red versus blue. Now I can project it back to 2 dimension. If I project it back to 2 dimension, I get this one, right? Does everyone see that? So the idea is that whenever your data is non-linearly separable, mathematically, you have to go to higher dimension. And sometimes one higher dimension doesn't work. You have to go to multiple higher dimensions, right? If you watch the video, the visualization, I hope that you get a sense. But the idea is that in general, you have to go to higher dimension, find the separating hyperplane in higher dimension, and then project it back to lower dimension, and then you're done. And as you can guess, this is mathematically and computationally heavy. So in order to skip this, there's this beautiful trick. We call it Kernel trick. And the Kernel trick is going to go from this graph to this graph without going to higher dimension, finding the separating hyperplane. This is a very powerful method. Does the intuition clear? Because when it comes to these kernel functions, it is a little challenging and technical. I'm not going to talk about the derivation of them because it needs to going over the dot products between the observations. That's beyond the scope of the class. But intuitively, I hope that it's clear what the kernel trick is doing. It's doing exactly the same job, finding this beautiful classifier, nonlinear classifier, without going to higher dimension and projecting it back. So this is what the kernel trick is doing. Okay. And we have a bunch of different kernel tricks, but before looking at different versions of the kernel tricks, let's see what is the optimization problem, right? So SVM generalizes the SVC to a nonlinear model. So in terms of terminology, we know what is MMC, we know what is SVC, and then the generalized version of all the two is SVM. And it's doing the job by using a kernel. And I want you to think of kernel as a mapping function, but in the same dimensional space. It doesn't go to higher dimension, right? And then which is applied to the inputs, the x1, x2, x3. So the kernel is a function that quantifies the similarities between observations. So this is literally the definition of kernel by looking at the dot products, right? By summarizing the relationship between every single person in the training set. So at the end of the day, I want you to ignore the 3D version. Just focus on the in 2 dimension. The first here. Let's just focus here. The kernel is applying a mapping function to these observations. And it's going to assign one number to every single observation. And if those numbers are closer to each other, it's going to classify them in one group. And if they're farther from each other, it's going to classify them in another group, right? And it's going to come up with this nonlinear decision boundary. So this is how the kernel, at least intuitively, is doing a job, okay? And the optimization problem, this is exactly the same as SVC. What's the difference? I highlighted it in red. SVC, the kernel is linear. So in SVM, if the kernel function is linear, W1 x1 plus W2 x2, we call it SVC. If the kernel is nonlinear, that's SVM. So I want you to always, from now on, always use SVM to support vector machines, but be aware that what's happening behind the scene, right? And when you're tuning the hyperparameters, we will find the optimal kernel. If it is linear, we will find the optimal cost, C tuning parameters. And then for some kernels, like RBF, we're going to find the gamma as well. So let's look at a bunch of these kernel functions. The most commonly used one is something called RBF, radial basis function. What does it do? So RBF is based on multiple Gaussian distribution. So I think all of us are familiar with normal distribution, Gaussian distribution, right? If I do multiple normal distribution, it's in 3 dimensions, something like this. Is this clear? Right? There's a functional form for that. It's very straightforward. And then I'm going to, so this is what we call RBF, radial basis function. So let's look at an example. in 2 dimensions. So let's say this is the data, and I want to apply RBF kernel. So as I said earlier, guys, at the end of the day, when you apply any of these kernels, it's going to assign one number to every single observation. How it's doing that? For RBF, this is a function that's going to derive that number, right? So it says that there's this L, we call it landmark, and the landmark is this red circle. So this is our landmark. And you can put the landmark differently in different part of the data. There's an optimization problem for that itself, but again, it's beyond the scope of the class. We're going to use Python, just change the kernel, put it in RBF. It's going to give us the output, but I want you to understand the intuition at least. So in this case, so landmark is right in the middle. So this is our landmark. This kernel function is going to find the distance between every single point from the landmark, right? If the points are very, very, very far from each other, what's the value of k? Is it large or small? If this number is large, the x and l are very far from each other. E to the power of minus something is going to be small, right? Yeah. Okay. So this is e to the power of minus. Okay. So in this case, the k's are smaller. So here the k's are larger. Can you see that how easily the kernel function can say, okay, now let's put these k's which are large together and the smaller ones are together without going to higher dimension. This is really important. I want you to understand we're not going to higher dimensions. All the calculations are done in 2 dimensions in this example. So this is the beauty of kernel tree. Without going to higher dimension, we can do the job by staying in the same dimension. And by applying some kernel. So in this case, the kernel is RBF, Gaussian RBF or radial basis function. And the hyperparameter that we're going to tune in Python, we call it gamma. And it's very straightforward. So gamma is the inverse of the sigma. And guys, this is our friend normal distribution, right? If sigma is large, well, this is if sigma is small, if sigma is large. Does everyone see that, right? If sigma is small, we are reaching out to closer observations, right? If sigma is large, we are reaching out to further observation. So just think of, for gamma, if gamma is large, what does this mean? Sigma is small. If sigma is small, we are reaching out to closer observation, right? Closer to the landmark. Does everyone see that? So if gamma is large, closer, more local observations. If gamma is small, further neighborhoods. So here, I think this picture put it very perfectly. So imagine these are the classes. So if gamma is 0 versus gamma is 100, right? As you can see, if gamma is large, it means that our sigma in RBF is small. You're reaching out to closer points compared to when gamma is small. Does everyone see that? This is clear? Okay. So in the remaining couple of minutes, let me show you at least different, most common types of kernels that we use. So the linear, this is our linear kernel. If this is a kernel, if the kernel is linear, basically we're talking about SVC. Then RBF, we saw the hyperparameter for RBF, which was a gamma. We will deal with polynomial kernel and sigmoid kernel. So these are the most commonly used one. So how can you do it in Python? We're going to say that, okay, Python, just try linear, RBF, poly, and sigmoid. And at the end of the day, you compare the error rates and see which one is doing a better job. Okay, application-wise, it's super easy, but intuitively, so this is how we did the classification using RBF. This is how we do it using sigmoid. This is how we do it using polynomial. Again, at the end of the day, the hyperplane in 2 dimensions are going to be different. So let's look at this one and conclude it here. So if I imagine the classes are, let's say, dark blue versus green. And if I use linear kernel, so this is my hyperplane. Hyperplane is going to be still linear because I can call it SVC as well, right? If I use polynomial, again, in 3D, it's something like this. In 2D, if you look at the projections, whoops, not you again. If you look at the projections, in 2D, it's going to be like this. So this is our beautiful nonlinear classifier. And this is the to the power of 2. If I have third polynomial, as you can see, it's going to be more nonlinear. And this is our radial basis. You see, look at that, depending on how I define a gamma, if it is large or small, I can reach out to closer or further observations. And guys, look at that. In this example, I have two landmarks. Landmark 1, landmark 2. So you see how powerful is RBF? If your data is something as weird as this, you can place the landmarks in different places of the data and figure out and come up with the classification. This is very powerful. Okay, so you can simply do that K1 plus K2 in this example. K1 is using L1, K2 is using L2. Very good. And finally, sigmoid. Again, this is a projection of the previous one. All right, so let's pause here. Yeah, let's pause here. And next class, we're going to do support vector regression. And yeah, the last slide is talking about logistic versus SVM. So I'll cover this one next class. All right. So is there any question here? So I made a slide out of the questions. So I'll go over those slides at the end of the next class. So let's see. Yes, sir.
For the homework assignment,
Yeah, let me pause this one because I had something to add for the homework.